is back to the plus and minus basis. So you get something like this. So you can do the same thing for 3 qubits, for example, and then 4 qubits and so on. But as you can see, when you try to, if it is a small number of qubits, then basically you can just calculate like this. But if the number of qubits become larger and larger and larger, then eventually it's very hard for you to keep track of everything. So that's why people usually use the stabilizer formalism when they try to specify your cluster states. And there's a very easy way for you to identify the stabilizers. So,
Wait, Choong, wait. Can I ask?
right,
So for these three, okay, so you have a 0, 0, plus, plus. But what why are you having plus 0 plus there? A minus 1 again?
sorry, minus one.
This one in the cat. So you have plus 0 plus.
Uh-huh.
This is for 3 qubits. So you
Yes.
consider, oh, you're putting also the qubits as well, 0 and 1.
So for 3 qubits, for example, so
Mm-hmm.
the diagram will
One,
become one,
one,
two,
two,
three,
three. Yes,
and
uh-huh.
then I'm just considering the one-dimensional cluster states. So
Mm-hmm.
qubit 1 is connected to qubit 2, qubit 2 is connected to
To qubit
qubit 3.
3.
So
Okay.
basically, the kind of the order does not matter because
Uh-huh.
if you do, let's say, 3 to 2 and then 2 to 1 is the same as 1 to 2, 2 to 3.
Okay.
So in this case, we already did 1 to 2.
Okay.
So what we need to do is 2 to 3.
Okay. So you
Then
have to
so
submit.
meaning you cancel out another plus, and then the second qubit you need to expand it, and then
Mm.
you do control Z
So that
with the
that's
third
that's
qubit.
okay, okay. Then you have these combinations of 0 plus 1 minus.
Yeah.
Okay.
Then you after you do all that control Z thing, you just simplify it back. Then
Okay,
you
okay,
find
okay.
this.
All right, all right.
So as you notice, there's actually some kind of patterns
Mm-hmm.
when you sort of like add in an extra qubit. You see that it's sort of like a linear combination for the zero part, and then for the one part is sort of like you change a little bit of the sign. So I calculate up to 6 qubits, you can still see the pattern. Okay, so another way of writing the cluster states is basically by the symmetry. So the kind of symmetry that we are considering is the stabilizers. So essentially what we are required is if let's say we are applying some unitaries on your quantum state, uh, it always gives you back the negative states. So in other words, your eigenvalue should be plus one. So the the thing that I write here, global phase matter, meaning that it cannot be minus one. It has to be plus one in this case. So then, if we consider, let's say we have U and V, they are both stabilizing your quantum state, then their product will also be the stabilizers, and the inverse will also be the stabilizers, and identity matrix stabilizes everything. So because of you have matrix multiplication and then inverse and so on, basically the set of all stabilizers they form a group. So because we are so used to Pauli matrices, we know the algebra of Pauli matrices, and then basically they are also the quantum version of classical gates, and the behavior is very well understood. So that's why usually we are using Pauli matrices. So if you study one by one what kind of state they stabilize, so identity matrix stabilize everything, your x will stabilize plus, your minus x will stabilize minus, and then your z will stabilize 0, minus z stabilize 1, the y will stabilizes I, minus y will stabilizes minus I. So then uh, if you have multi-qubit states, basically your stabilizer will just be a tensor product of your Pauli matrices. So for the first example, if you have 0 and plus, so basically the stabilizers will be identity, and then is either the x on the second qubit or z on the first qubit, or the tensor product between the two. So this is easy to identify. For the second example, basically your stabilizers will be this set. As for the third example, which is a cluster state, your stabilizer is this set. So you can verify one by one the stabilizers. So in general, if you have a n qubit stabilizer states, then your stabilizers group will have 2 to the power of n elements. So this is easy to see because we look back at 1 qubit. So basically 1 qubit is you're having like 4 elements in the stabilizer kind of no, sorry, uh, we just look back here. So essentially for 1 qubit, let's say you're from 0, basically you just have identity and z, right? So it's 2 to the power of 1. So if you have a tensor product of n qubits, so essentially you are just multiplying 2 n times, which is why you have 2 to the power of n. And then one interesting thing that we know is that we don't actually need all of this. Essentially, we just need the generators. Then we already know what kind of stabilizer groups that they are in. So meaning that for some n qubit stabilizer states, the generators is always by only n elements, is up to plus or minus sign. So usually we don't actually look at the plus and minus sign. So for example, for the cluster states, usually we are just specifying xz and then zx. And then identity and y tensor y is sort of implied. So similarly for these bell states, we usually just specify xx and zz. So then we can try to sort of like calculate how many bits that we need to specify uh, stabilizer states based on the stabilizers. So if you have one generator of n qubit states, essentially because we either want x or z, so that you need like 2 bits to specify is either x or either z, and then you have n Pauli matrices, so that's why you have 2 times n. And then this plus 1 is just to specify the sign that you're using is either plus or minus. So this is for one generator. So in general, if you have n qubit states, you have n generators. That's why you multiply them together and you get 2n squared plus n. So this is of order n squared. So we only need like n squared terms to specify stabilizer states based on the stabilizers. But if you look at, if you want to specify a normal quantum state by just the state vectors form, then we need 2 to the power of n bits. So that's why you can already see the efficiency of using stabilizer formalism in this case. And there's one very powerful theorem by Gottesman and New. Basically, they say that if your quantum circuit is prepared in a computational basis, and then you are only using the Clifford gates, which is the Hadamard, the CNOT, and the phase gate, and you measure your states in the computational basis, then essentially you can simulate this quantum circuit on a classical computer. So meaning you can calculate whatever is happening using quantum computer. So there's one algorithm provided by Harrison. So essentially, uh, just trying to show how you can make use of this theorem to keep track of your stabilizer states.
Sorry, Choong. So it means that you can just compute or simulate your quantum circuit in classical computer, right?
Provided that you are using
Provided,
these three conditions.
All right,
Yes.
all right.
So, uh, so this is provided by Harrison. So essentially, we just want to keep track of the stabilizers. So we begin by having this kind of matrix. The left hand side is called the X matrix, the right hand side is called the Z matrix. So whenever you have a stabilizer in X or Z, the the entry will be on a Z x-axis will be 1, otherwise it will be 0. So whenever your stabilizer is either Z or Y, then your entry on your Z matrix will be 1. So this is how you identify your stabilizers. And then because we can only perform Hadamard, CNOT, and phase gate, so this is what we study. So we study the effect of these three gates on the matrix. So if you have a Hadamard gate to the I qubit, so essentially because we start with computational basis, so essentially we are changing from the X to the Z basis, right? From 0, 1 to plus and minus. So that's why what we need to do is to swap the I column of your X matrix to your Z matrix. If we do the phase gate, then essentially the effect is to perform the XOR from X to the Z matrix. So if you perform a CNOT, then you need to do two things. You need to XOR from the X matrix to the X matrix, and then from the Z matrix to the Z matrix. So the reasoning for CNOT is as follows. If you look at the effect of CNOT in computational basis, essentially it changes these two. So that's why you need to swap from I column from your X matrix to the J column with your X matrix. You need to do the XOR. But if you look at the Hadamard basis form, so you see that if you perform a CNOT, so it is as if when your second qubit is minus, you change your first qubit. So meaning that you have to do the opposite direction as well. So that's why when you have CNOT, your XOR is from I to the J at your X matrix, and then you also need to do the XOR from the J to the I column in your Z matrix. So that's the reasoning for CNOT. So now if you look at the example, so we begin from 0, 0. So the stabilizer for this is easily identified. It is Zi and then Iz. Uh, Slightly abuse of notation. This is actually the generators. So now we are only tracking the generators. We don't need to track the whole stabilizer group. So because there's no X, so your X matrix is 0, and then your Z matrix is basically 1, 0, and 0, 1. So if let's say we want to get a Bell pair, sorry, this should be 1, 1, slightly typo. So we first need to perform Hadamard gates on the first qubit, and then CNOT from the first qubit to the second qubit. So if we do the Hadamard, Hadamard is essentially swapping. So I swap the first column of your Z matrix to the first column of your X matrix. So it becomes like this. And then we perform C naught. C naught meaning that we do XOR from the first column to the second column. That's why we get 1, 1 over here. And then from the second column to the first column on the Z axis, so which is 1, 1 over here. So then we read out the final form, whereby the generators is basically XX and ZZ for a bell pair. So notice that in this example, basically I don't track the plus and minus sign because I think that will be slightly more complicated. But this is just to show that you can just study your stabilizers without looking at your quantum state. So also because of this theorem, it basically means that whenever you have a stabilizer state and your operations are also stabilizers, then essentially it means it is somewhat easy operations because you can always simulate in a classical computer. But now, if you have some gates that are non-stabilizers, then from the computational perspective, it is difficult because you cannot simulate this on a classical computer. So that non-stabilizerness is what we call as the magic, if you know about the term. So I think that's all that I have for today.
Oh, thank you, Choong. This non-stabilizer, one of them is what? Magic gate, is it?
Not magic, magic sticks.
Magic states, sorry, magic
Yeah,
states.
yeah.
I think for the Clifford, if we mention that the Clifford gates, they falls under Clifford groups as well, is it?
Yes.
So,
So Hadamard, CNOT, and Facegate basically they are the Clifford group.
and so the
And
actions is only on Pauli, right? So they act on Pauli and make sure Pauli doesn't change. Is that it?
yeah, I think Pauli is a normalizer, right?
Pauli and normalizer, yes.
Yeah,
Yes.
the Pauli group.
Pauli groups.
There's a whole new topic on Clifford groups and then Pauli groups.
Yeah.
And,
Because when we talk about the stabilizer, we also have a group stabilizer, right? The group stabilizer in group theory is definitely don't change the elements, right?
yeah,
Whenever you
that's
do
why that's
actions,
why you begin with the stabilizer equation.
the stabilizer equations.
Yeah,
So somehow rather it's like your stabilizer equation, somehow like your eigenvalue equations, but over here always the eigenvalue plus one.
yeah.
Okay.
I think there's a whole lot of topics in the Clifford gates and
Clifford
Pauli, basically the Clifford group, Pauli group, and then there's another thing called the universal gates.
universal gates.
So
Yeah.
Clifford gates, as shown here, is not universal gates because it lacks something. You need to either add the Trofoli gate or the pi
Okay,
over
okay.
8, pi
Oh,
over
okay.
8 kind of rotation gates so that it become universal. So meaning that with just these three elements, you cannot really create whatever quantum state that you want. You're only going to a certain quantum state called the stabilizer states.
Universal states.
Yeah. So that's why I think from a geometrical perspective, there are a lot of things that we can study here.
Oh.
And this is not unique actually. Okay, most of the quantum error codes, they are stabilizer codes because
Correct.
it's easy for you to calculate and to look at things. So that's why stabilizer formalisms are important in
QC.
PVC, yes.
Mm. Yes. I think his kid IBM have this stuff. They relate so Pauli and thing you can test simulate classical computer.
Yeah.
But I have questions. So these facts,
Mm-hmm.
there seems like there's some conditions. I remember when I study groups, it's like what we call this. Is it like sufficient necessary conditions? I mean, to find, for example, the size of the groups or whatever. Especially facts number 3 there. Is
Mm-hmm.
there any relations to groups in particular? Facts 3 here.
I think over here is not exactly the group part. I think 1 and 2 is actually coming from group theory.
From groups, right?
Yeah, because
Okay. What?
you talk about the size of a group and
Uh
then
huh.
the size of your
So the
stabilizer.
first one, facts 1, size, right?
Yeah,
Okay. Number
the
2,
size of your stabilizer group. The second one is the size of your generators.
size generators.
Yeah.
But
Uh,
number 3 is what? What is another conditions? This one?
I think number 3 is basically just like to show how how using stabilizer formalism is easier
Compared to the first one,
compared
right?
to if you calculate this one by one
By one.
is very tedious because okay, for cluster states, once you know the stabilizer formalism, it's very easy.
Very easy.
So basically, how do you identify the generators? So is you look like this. So you look at the first qubit. If it is linked to the second qubit, so it will be the second qubit will be your Z,
Yeah,
and then
that
the first qubit
first
will be
big
X.
X, correct.
Yeah. And then if let's say, and then you look at your second qubit, so now your second qubit is X, your first qubit is Z.
Is that
So that's why you have XZ and then ZX. And
okay?
then the rest, so this will be the generators, and then these two you can generate from XZ and ZX.
Somehow it's related to KY. KY works also have this RX, but it's have these 3. But do you have from here? Do you have XY tensor of XY? I never see. Sometimes in literature, mostly X.
Usually it's exact.
Yeah, usually it's exact.
If you do the reduced density matrix, then maybe you
Oh,
can have exact x1.
then we can have XY.
Yeah, it's possible to have x1.
Okay, I think in most literature examples, I think exact is easier compared to XY.
Uh,
I don't know.
because x is bit flip and then z is just a
Yeah,
phase change.
let's
So yeah,
flip and change.
those are the most intuitive ones.
Oh, okay. All right. This is interesting. Okay. So, anyone, if you have questions, maybe you can ask us. I have one more from this part. Okay, go ahead. Anyone?
I got questions.
Okay.
Choong, how, what is the definition for stabilizer? Can I have a look? I'm still
Stabilizer
confused.
basically, okay. Stabilizer basically is all the elements U such that it satisfies this equation.
You mean identity?
Uh, yeah, that's why identity stabilize everything. So because identity multiply with your state,
Stabilize.
you always get back your state. So for example,
You
if you have,
rotate the state, rotate, and you also can get back.
okay, if you look at Z, Z is 100 minus 1, right?
100 minus 1.
Uh,
Multiply this with zero, so you
Because
multiply with 10.
maybe we look at the
this
Pauli.
one is column vector.
Yeah, your cat 0 is 1, 0.
Column vector or row vector.
So your Z is this, right?
Mm-hmm.
So if you have 1, 0, which is your zero state, so when you multiply it, you always get back 1, 0. So that's why it satisfy
Okay.
this
Because this
equation.
is a matrix multiplication.
Yes.
So
Yes.
you can get the get the
Yes.
same vector. Okay, matrix.
Mm.
Okay.
Yeah. Can you go back at the stabilizer just now?
Which one?
All the list of which stabilize which.
Okay. Here.
Oh yeah, Z only stabilize. Okay, yeah, minus we stabilize 1.
Yeah.
Because your 1 is 0, 1. Yes, then you get the same back as 1. Yes, because you have 0 minus 1. Yeah.
So basically, another way of saying this is basically your Z, the eigenvectors is 0 and 1, right?
Yeah,
So you have eigenvalues
correct.
plus 1 and minus 1.
Yes.
So you just put that minus 1 to in front.
Why you got iCat? iCat, what is iCat?
Oh yeah, I was supposed to ask that one.
I think it's
Is
0
cat
plus I1 divided by square
0,
root 2.
0
So
plus I?
you got
Oh, you
So
mean the superpositions we're having a complex number? The I cat.
yeah, it's 0 plus I times
I
1 will
cat
divide
1.
by square root 2.
Okay, so maybe the cat plus is cat 0
0
plus
plus
cat 1, right?
1, yeah, 0 plus 1 divided
Mm,
by square root 2.
by square root 2. Okay. Oh, so cat I is you having cat 0, you have the 1 over square root 2, cat 0 plus I, cat 1,
Yeah,
right?
you have that extra relative phase.
Okay. So I think
this spaceship, right?
standard only these 3 code. You have more? You have plus minus 0, 1, I. Do you have more? Or this
No,
is the most common?
usually the
This
most common is this
this is one, right?
plus or minus and then 0, 1.
Then 0, 1, and then I.
Yeah.
Okay. Okay. I have questions page slides number 9.
Mm-hmm.
When you say in order to obtain a bell pair, okay, I know you have bell pair 0011.
No, this is not 0, 0. This is 1,
Yeah,
1.
1, okay. So in order to obtain, does this over here means that you correct, or sometimes I have problems to use is it like you're correcting or what?
No, if let's say you start with 0, 0,
Uh-huh.
so you want to get the bell state.
Okay.
Yeah.
So you
Then
start with a 0, 0 over here. I can say like
the
cluster
initial
state
state.
1 and 0. 1 and 2. Can I say that?
Cluster state
This
1 and 2.
is it sorry. This one 0, 0, so it seems that you have 2 qubits, right?
Yeah.
Okay, then you want to produce the bell pair from just 0, 0.
Yes.
Oh, okay.
So what you need to do is Hadamard the first qubit and then C naught from first to second.
Okay.
So if let's say now you're doing this cluster state,
Uh-huh.
so because the initialization is in plus, right?
Plus, okay.
So if you start from 0, 0, so the first step is
Uh-huh.
you apply Hadamard on the first qubit and the second qubit, so that they
First,
become plus plus.
okay. Difficult to imagine. Wait.
Then you do the CZ.
So I have to go is I start with 0, 0. I have to get the plus plus first
Yeah. So you do plus Hadamard on both qubits.
on both qubits.
Yeah.
Okay.
Then you do the CZ. The problem here is that because the Clifford gate that they use is C naught. So I think we need to study like the effect of ZZ on the basis similar to like this.
Uh-huh.
So you need to study the effects and then see correspondingly how you need to change your matrices, like how you need to transform your matrix elements.
Okay.
Yeah.
So let's say if I start with the initial state was 1 1, can I still get in order to obtain a bell pair?
I think you will get a different bell pair.
A different bell pair. Ah,
It's not the 00 plus 1 because bell pair you have
for different.
four different bases, right? Bell
Yes.
bases. So I
Uh,
think you'll get a different one.
okay. So in order for that, I mean, for me, for an exercise, I can start my initial state 0 0 or 0 1 1 0 and 1 1, right? I can produce such.
Yeah.
Ah.
So this is the particular example that I
Okay.
use,
Okay.
but you can always use others. But
Uh,
I think you also need to be careful a little bit because here I don't trace the plus and minus sign.
oh.
So
Uh,
if you start from 00, the the generators should be minus I zi and minus iz. But the problem with the example given in the notes is that they don't trace the plus and minus sign. So I'm still studying like how to trace the plus and minus sign.
plus minus. Oh, okay.
Yeah.
That's why it is. Is this plus minus signs according to the parity thing?
What parity?
I don't know. Is it related to all these classical versions of uh, well,
So
when you write
what is the
stabilizer?
plus minus indicate?
Okay.
What is
So
the meaning of plus minus sign?
this
The
one.
plus minus sign is over here.
This one. Which
So
one? The cat. The one in the generator.
the one in the generator.
The one in generator.
So the only problem is that when you do this, so the algorithm did not actually specify how to deal with the plus
Oh,
and
plus
minus sign.
minus sign.
Yeah. So I think the explanation should be quite difficult because he didn't include in the notes. So
Okay.
I'm kind of like still thinking about it.
But does that means when you write down the matrix form for x and z, if
Mhm.
we consider the plus minus sign, can we include the plus minus sign as it is here?
Uh,
Let's
I
say we just multiply with each of the elements. Let's say if we have minus z, can we have like minus one
I
somehow?
think I think it might be possible, but perhaps you have to change the rule a little bit because when you let's say perform the XOR,
Oh,
there's
there's
actually no
no plus
minus one.
minus.
Yeah,
Correct,
it's,
correct, correct,
it's zero
correct.
and one. So I think you need to change the rule a little bit, but I think it can be done.
Oh, okay, okay.
Yeah.
Uh, all right. Okay. Okay, I have no more. Okay, one more question. When you write stabilizer with this curly bracket thing, so it means what? It means
The generator,
generator, is
the generator. Yes. Slightly abuse of notation already.
it? So for this one, your stabilizer, so you have two generators. Is that what it
Yeah,
means?
because if it is the origin, like okay lah, generators lah. If it is stabilizer, you should have four elements.
Okay, 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 okay. All right, all right. Generators.
Hello, hello. I would like to ask,
Yes,
Alright,
sure.
Dr. Chong.
uh, just call me
Uh,
Choong.
in equ in equation 3,
Mhm.
so the right hand side of the square matrix is the identity matrix. Is it? Or
Mm, in this case, you can say it's identity matrix, but it doesn't mean anything. It is just a way for you to trace how the stabilizer transform.
is equation 3 uh the stabilizer Zi? or it is not?
Okay, so over here the first rule is when your stabilizer is Z, your entry is 1. So it's Zi, so this is 1, this is 0. So you're reading row wise. So meaning this represents the stabilizer for your first qubit, this is your second qubit. So you have two stabilizers, so it's Zi and then Iz. So you don't have any x, so this is 0, 0. So if let's say your stabilizer has, let's say xy, let's say this is xy, also, let's say, for example, if your stabilizer, the first one is y, then this has to be 1 as well.
1.
Because this
Pauli
one,
matrix.
yeah.
Is it Pauli matrix? No.
Okay, because when the first row is 1, so meaning that you actually have xi, and then the second part is zi. So if you multiply x and z, you get back your y. That's how the rules are made. So if you read back the rules, why they include the y inside is because if let's say your stabilizer contains y, you actually can multiply your x and z to get back your y. So this is the reasoning.
Can I see the previous slide? Number 2 or number?
Which one?
I think the second slide.
Yeah.
Oh, third.
Mhm.
Okay, so the stabilizer equation.
Mhm.
So is U a kind of operator? Operate on a state
Yeah.
that
In
does
this
not
case, you can just think of this as a unitary matrix.
unitary matrix
Yeah.
is a square matrix,
Yeah.
right? So the state is a column. The cat is the column matrix.
Yeah.
So the next slide. So if U and V stabilize, so the stabilizer, is it a kind of operator also?
Yes, but in this case, we just think of it as matrices because like it's easier to think of it as matrices. So they are operators basically.
So at the next slide, uh, what is the meaning of the n fact one, the n qubit stabilizer states? I thought it is an operator.
Oh, meaning the stabilizer states has n qubit. So I mentioned before that stabilizer states you can only you can only travel to a certain states if you use just the Clifford gates, these three operations. These three operations. If you stick to these three parts, you can only travel to a certain states. So those certain states are called the stabilizer states.
Stabilizer
So
state.
like this one is stabilizer states, this one is also
Oh,
stabilizer states.
oh, okay.
So I think, Choong, if in this case your n is just 2, right? 0, 0. So you have
Yeah,
2
over
to power
here
of
I
2,
just
so
use
4.
two. Yes.
That is the what is the maximum for we able to simulate? So do you have like maximum n stabilizer states, n qubits?
Uh,
How many n
from
we can go up to?
from Aaronson's notes, he said basically the limit is the power of your computer.
Oh, power of computer. I see.
Yeah.
So you can go more lah if you
Yeah,
go
you can go like
supercomputer.
a very large size.
Very
But
large and
it's very stable. It's only for stabilizer states.
only for stabilizer states.
Yeah.
Okay. Okay, wait, so just now, we have stabilizer state, so it works with the rest. So non-stabilizer states means that you cannot apply the stabilizer equations, right?
Uh,
Is that how we should?
you can, if it is non-stabilizer, meaning that it's either what you are saying or you add in a group which is not from this Clifford Gates.
Oh.
So meaning that that's why Clifford Gates are not universal gate state because there are some states that you cannot travel to. So those states
Okay.
that you cannot travel to is the magic states or non-stabilizer.
So
So
that's so the magic states the non-stabilizer, right?
yeah, non-stabilizer. And then if you want to go more into the resource theory part, basically non-stabilizerness is a resource, just like entanglement. Yeah, because you have something that is easy to execute, which is your Clifford Gates, because you can simulate in a classical computer. And then you have something that you cannot simulate with a classical computer, which is your non-stabilizerness.
So that one really need quantum computer to simulate.
Yes. So that will be a resource.
Oh, okay. But for the non-stabilizers, then we don't really talk on the stabilizer equations, right? So we have something
Yeah.
else.
Yeah.
Okay. All right. Thank you.
Anything else? If not, then
Yes.
maybe I think we can end